In section 4.4, we're going back to discussing limits, which we did much earlier in the semester. The reason why we're going back there now is there were certain limits that we were unable to evaluate when we were first studying limits. And we're going to learn a technique here that will help us evaluate some of those types of limits. And the reason why we waited on this method is because this method involves using the derivative, which we hadn't learned at the time when we were first looking at limits. When we studied limits earlier, we saw that we always try to use direct substitution. That's the easiest way to evaluate limits, but it doesn't always work. All right, so if you remember that idea, if it's a piecewise function, we know we can't use direct substitution, but if it's one of our other types of functions, we always try direct substitution first, but if you end up getting 0 in the denominator or it's just undefined in some way, that means direct substitution does not work and you need to find another method, because it's still possible the limit exists even if direct substitution fails. So here's some examples of types of limits we've seen before where direct substitution did not work and we were able to find other methods. So look at the first one. This is rational, and when we try to evaluate the limit by substituting in 1 for x, notice we get a 0 in the denominator. So we can't use direct substitution. But let's think about what happens to the numerator and denominator separately. So as x approaches 1, the numerator is x plus 2, so it's going to approach 1 plus 2, which is 3. So the numerator is getting closer and closer to 3. And then in the denominator, as x gets closer and closer to 1, this expression gets closer and closer to 1 minus 1, which is 0. So individually, we see the numerator is approaching 3 and the denominator is approaching 0. When you end up with a non-zero divided by 0 in this analysis, our fraction is looking like this, a non-zero number over 0. We saw this concept earlier that if the denominator gets closer and closer to 0, that makes the fraction get bigger and bigger. And since the numerator is just approaching a finite number, and that's not 0, and the denominator is getting closer and closer to 0, that means this fraction is getting infinitely large. So we can, in this situation, we conclude this limit is going to infinity. We'd have to do a little more analysis to determine if it's plus or minus infinity, but we know it's infinite. Okay, so that's an important thing to remember that will help you with limits. If the numerator is going to a non-zero number and denominator is getting closer to 0, that means the fraction as a whole is becoming infinitely large. Now let's look at the second example. Another rational function, and if we substitute in 2 for x, we're going to get 0 in the denominator, so this one we can't use direct substitution. So let's try the same thing we did with the first one. Look at the numerator and denominator separately. So here the numerator gets closer and closer to 2 minus 2, which is 0, and the denominator gets closer and closer to 2 squared minus 4, which is also getting closer to 0. So this time, top and bottom are both going to 0. This is an example of what we call an indeterminate form. And we're going to look at several indeterminate forms. This is one indeterminate form. There are others. So why is it indeterminate? And when we say indeterminate, it means just looking at this form is not enough to deduce what the limit is. Up here, this is a determinate form because looking at this, we were able to conclude the limit was infinity. Okay, so I'll just mark this. This form is determinate. We can figure out the limit just by looking at that. Now let's go back to the bottom one. Why is it indeterminate? The denominator going to 0 makes the fraction as a whole get larger and larger off towards infinity. But the numerator going to 0 pulls the fraction towards 0. So they're competing against each other, and we don't know which one is going to win. If the denominator goes to 0 faster than the numerator goes to 0, then the denominator would win, and the whole fraction would go towards infinity. If the numerator is approaching 0 faster than the denominator, then the numerator would win, and the fraction as a whole would go to 0. Or if they're going to 0 at about the same pace, they might compromise and balance out somewhere in the middle at some finite number other than 0. So that's what I mean by indeterminate. The form enough, just knowing that top and bottom both going to 0, that's not enough to conclude what the limit is. Now we saw limits like this before, and we saw that a technique that sometimes works is to try factoring. So notice here the numerator or the denominator factors to x minus 2 times x plus 2. And now notice there's a common factor of x minus 2 that can be canceled. So when we rewrite the limit after canceling those, we're now just looking at 1 over x plus 2. We try direct substitution again, and this time there's no problems, right? Because we get 4 in the denominator. So if it's defined, we know the limit will just be what we get from direct substitution. So we get 1/4 is this limit. Okay, so these are two cases we've seen of how to handle situations where direct substitution doesn't work. And we're starting to see this, what we call the form, what the numerator and the denominator are doing separately. And sometimes that form tells you what the limit will be, like in the first one. In other cases, the form is not enough to tell you the limit. So we're going to be looking more at these indeterminate forms in this section. Here's another situation where we can't use direct substitution, and that is if you have a limit at infinity. So if you remember that expression, limit at infinity means x is approaching either plus or minus infinity. So all three of these are limits at infinity. And we've encountered some of these, I think all of these situations before, maybe at least 2 of them. So let's go through these 3. On the first one, as x goes to infinity, we want to determine what happens to this expression. So if you just think about the situation, if x is getting bigger and bigger and bigger, infinitely large, then x squared is also getting really, really big, right? It's even bigger than x. And the same thing here. If x is going off to infinity, then 2 times x would also be going off to infinity. So if we wanted to write the form like we were doing on the previous slide, this would be the first term goes to infinity plus a second term that goes to infinity. And so then we're adding together 2 numbers that are both getting infinitely large. So the whole sum would also be getting infinitely large. So that form is determinate. We can conclude, based on that form, that this limit is infinity. Okay, so infinity plus infinity, this is a determinate form. Okay, let's go to the second one. So in this case, the numerator is fixed at 2, And then if we think about the denominator separately, as x gets bigger and bigger off to infinity, x minus 1 is also getting infinitely large. Right, 1 less than infinity is still infinity, right? So if we look at the form, meaning look at the numerator and denominator separately, the numerator is a constant, so we would just say the numerator is approaching 2. Denominator is approaching infinity. Now think about a fraction that's kind of like that, right? Numerator 2, denominator getting bigger and bigger and bigger, like 2 over 100, 2 over 1,000, 2 over 1,000,000. That fraction is getting closer and closer to 0 as I keep increasing the denominator. So that form is enough to figure out what the limit is for this one. This limit would be 0. So that means this is another determinate form. We're able to figure out the limit just from that form. Look at the third one now. So as x gets bigger and bigger off to infinity, notice the numerator, both terms there would be getting infinitely large, so the numerator is going to infinity. And then the denominator would also be going to infinity. So the form here would be infinity over infinity. So the numerator going to infinity makes the fraction get bigger and bigger. It's pulling the fraction towards infinity. But the denominator going to infinity, like we saw up here, it pulls the fraction towards 0. So the two are competing against each other, and we can't tell which one's going to win. Just like with 0 over 0, they were competing against each other. One was making it bigger, one was making it towards 0. So here, if the numerator is going to infinity faster, it could pull the whole fraction towards infinity. If the denominator is going to infinity faster, it could pull the whole fraction towards 0. And if they're kind of balanced, then they might level off at some other finite number for the limit. So this is another indeterminate form. Now, we've actually seen a limit like this before, and the technique we used was, let's first write the limit as it is. So we learned a technique that works only in a very specific situation, and that is a limit of a rational function, which is what this is, as x approaches either plus or minus infinity. And because we're in that situation here, we can use that method. So again, that method is you find the highest power of x that's in the denominator, in this case x squared, and then we divide top and bottom by x squared. So here I'll make a note, that's what we're going to do in our next simplification. We're not taking the limit yet, so keep writing the limit sign. Now in the numerator, we're dividing both of these terms by x squared. So the first term will just become 3. And the second term, 4x over x squared, we can cancel a factor of x, and it simplifies to 4 over x. So what we have is 3 plus 4 over x. In the denominator, when we divide x squared by x squared, it becomes 1. And then we have minus 1 times 1 over x squared. Now we start looking at this simplified version and thinking about what happens to each term as x goes to infinity. So these two are constant, so they're just going to stay constant. But these other terms that are constant over x to a power, we know those are going to 0, right? Because numerator is a positive or is a non-zero constant, and actually just any constant, and the denominator going to infinity pulls that fraction towards 0. So those two fractions go to 0. So in the numerator goes to 3 plus 0. Denominator goes to 1 plus 0, 1 minus 0. And so notice the denominator is not 0, so this is perfectly defined, right? So this limit would be 3 over 1, which simplifies to 3. Okay, so we saw 3 more cases of situations where direct substitution doesn't work. 2 of them turned out to be, when we looked at the form, they were determinate forms, and we were able to figure out what the limit would be just from the form. The third one, the form was indeterminate, but we remembered we had learned a method to handle this situation, and we were able to figure out the limit anyway using another method. So let's summarize what we saw about these indeterminate forms. So first of all, if you're taking the limit of a fraction, so some expression in x over another expression in x, taking the limit as x approaches some number a, and if you look at the numerator and denominator separately and they both approach 0, right, that means the form is 0 over 0. We saw that was indeterminate, right? We said the numerator and denominator were competing against each other, so the form was not enough to figure out what the limit should be. So we refer to this type of limit as indeterminate form of type 0 over 0. Then we saw another type. Again, it was limit of a fraction, some expression in x over another expression in x, as x approaches a finite number. And when we looked at the numerator and denominator separately, they were both going to infinity. And it doesn't matter if they're plus or minus infinity, either one. Again, we said that form was indeterminate because the numerator and denominator were competing against each other. So this situation is called an indeterminate form of type infinity over infinity. So in both cases, the form is not enough to tell us anything. The limit may exist, it may not. You have to use other methods to determine what's happening with the limit. We also saw that we have already learned some methods that handled certain cases of these indeterminate forms, but those methods only work in some situations. What we're going to look at in this section are other limits where the methods we used before would not work, and we'll be able to apply these new methods to some of these examples of indeterminate forms. So this is the main method for this section that helps us evaluate limits with an indeterminate form, and it's called L'Hopital's rule. So it looks like hospital's rule, right? But it's actually the name of a French person, his last name, and so the pronunciation is L'Hopital, L'Hopital's rule. And so there's a lot written here, but let's start here. So this rule is used if you're evaluating a limit of usually it's a fraction, right? You can at least put it in the form of a fraction, and x is approaching a finite number. And you have one of those two indeterminate forms, either 0 over 0 or infinity over infinity. So that's described here. If the top and bottom are both approaching 0, that's the 0 over 0 form. And the second case down here, if both top and bottom are approaching either plus or minus infinity, that's the infinity over infinity form. So it's important to, before we even finish the rule, L'Hopital's rule applies only to these two forms. If you have any other form, you can't use L'Hopital's rule. Now, how do we use it? Here's the main rule right here. You can rewrite the limit that's indeterminate as a new limit. And the new limit looks almost the same. It's just that you replace the numerator with its derivative, and you replace the denominator with its derivative. So the rule here does not evaluate the limit for you, because it's still a limit, right? There's still a limit sign here. You still have more work to do to evaluate this limit. So what this rule does is it lets you rewrite the original limit. That's a difficult one. It lets you rewrite it as a new limit, and we're hoping that the new limit is easier. Maybe you could even use direct substitution on the new limit. Okay, so that's the basic of L'Hopital's rule. It lets you rewrite a limit that has one of these two indeterminate forms, lets you rewrite it as a new limit, and then you try to evaluate from there. So we'll do several examples now of this rule. And also there's some extra conditions listed here. The top and bottom functions, they have to be differentiable, and the denominator function, its derivative has to be non-zero on some small interval containing a, except possibly at a. And the other condition is this new limit has to either exist or be infinite. Okay, so now we'll do some practice with this rule. So actually, before we do some examples, I wanted to give you a partial proof of L'Hopital's rules, so you'll at least have some justification for understanding why it works. So it's only a partial proof because we're going to consider a special case, and that is we're assuming f of a and g of a are both equal to 0, f prime and g prime are both continuous, and g prime of a is not 0. So here's how the proof works. We're going to start with limit of f prime over g prime, and we're going to do a lot of simplification until we eventually show it's equal to limit of f over g, which is the original, or those are the two things we're trying to show are equal to each other. Now this first step is evaluating this limit using direct substitution, right? We kept f prime and g prime, we just plugged in a for x. Now why are we allowed to do that? How do we know direct substitution will work? Well, one is because g prime of a, we assumed it's not 0, so we don't have the problem of 0 in the denominator. The other is we assumed f prime and g prime are continuous, so that means the limit of f prime can be evaluated with direct substitution. That's the definition of a continuous function. So that means the limit of f prime of x is equal to f prime of a. Same thing for g prime because we assumed it was continuous. So that gets us to here. The next step is just going way back to our limit definition of the derivative. So earlier in the semester we defined f prime of a to be exactly this limit, right? It was the limit of this difference quotient. And then we do the same thing for g prime of a, apply the limit definition of g prime of a. Now the next step, we come over here. And notice the only difference between this part and where we rewrote was here we had the limit separate on the numerator and denominator, and here we pulled the limit out in front. This is using the rule about limit of a quotient is equal to limit of the top over limit of the bottom, which is what we have over here, as long as both of those limits exist, which they do because we assume these derivatives exist. Okay, so that gets us to here. So then in the next step, it just uses some algebra. If you multiply top and bottom by x minus a, that's just going to cancel, right? This x minus a will cancel with that one. This x minus a will cancel with that one. And so all that's left is the f expression and the g expression, like this. And then finally, we used our assumption that f of a and g of a are both equal to 0 to get here. And so now, like I said, we started with this expression, we kept simplifying until we got to this expression, which says those two things are equal, and that's exactly what L'Hopital's rule says. So like I said, this only proves the rule under certain assumptions. The rule can be proved in the way it was stated. It's just a much more complicated proof than we really want to get into right now. We're asked to evaluate a limit in this example. We always try direct substitution first, and notice that will result in 0 in the denominator. So we can't use direct substitution. So let's think about what we've been calling the form. So we look at the numerator and denominator separately. So we already know the denominator is going to 0, right? Because if x is going to 1, x minus 1 would approach 1 minus 1, which is 0. Now what about the numerator? If x is approaching 1, then the numerator is approaching log of 1, natural log of 1. And then hopefully we all know natural log of 1 is equal to 0. So the form looks like this: numerator going to 0, denominator going to 0. Now, this is not a rational function. It looks kind of like it's rational because it's a fraction, but remember, rational is a polynomial divided by a polynomial, and here the numerator is not a polynomial, it's a logarithmic function. So the method we learned earlier involved factoring, and that usually worked for rational functions. But here there's no factoring to do at all, so factoring is not going to work on this one. But the form is one of the two indeterminate forms. Right, this is indeterminate. The form in and of itself doesn't tell us what the limit is. But it's one of the two types of indeterminate forms where we can use L'Hopital's rule. Okay, so let's practice using the rule. So we're going to say this limit equals, and we're going to write a new limit. Still x approaching the same thing, which is 1. Now in the numerator, I'm going to put the derivative of the original numerator, which is natural log x. In my denominator, I'm going to take the derivative of the original denominator, x minus 1. Okay, so let's rewrite or simplify. I'm not taking the limit yet, so keep the limit sign. In this step, I'm taking the derivatives. So in the numerator, the derivative of natural log x we've seen, and we know it's 1 over x. The denominator, the derivative of x minus 1, is 1 minus 0, which is just 1. Now, before I take the limit, it would probably help if we simplified the fraction. Right, dividing by 1, we don't need to write that, so this is just the limit of 1 over x. Now, we've rewritten the original limit, which was indeterminate. We weren't able to evaluate it. We've rewritten it as this limit. This is now a rational function. We always try direct substitution first. And notice we get a non-zero denominator, which means we can use direct substitution. So we get 1 over 1, which simplifies to 1, and that's our limit. So normally you won't need to write this step, right? Normally you'll just go straight from here and then compute the derivatives and put them in. Make sure you keep writing the limit sign until you actually take the limit. So here, we use direct substitution to evaluate this limit, so as soon as I do the direct substitution, I remove the limit sign because I now have evaluated the limit. One other thing, because we're dealing with fractions and we're a quotient, right, and we're taking derivatives, you might get the idea that you should use the quotient rule. But that's not what we're doing here, right? We're not asked to find the derivative of this fraction. We're applying L'Hopital's rule, which says you take the derivative of the numerator separately, take the derivative of the denominator by itself. No quotient rule involved. Okay, so that's our first example of using this L'Hopital's rule. And again, you can see why we waited to cover this until after we learned about derivatives, because the rule involves taking derivatives. In this example, if we think about direct substitution first, if we plug in pi for x, notice the denominator will be 0, so we can't use direct substitution. So let's look at the numerator and denominator separately. As x approaches pi, the numerator will approach cosine of pi over 2. Now, that's basically using direct substitution for the numerator, and we can for the numerator by itself. Because cosine is a continuous function, that means you can evaluate the limit of cosine using direct substitution. Now, cosine of pi over 2 is equal to 1, so the numerator is approaching 1. Cosine of pi over 2 is 0, so the numerator is approaching 0. The denominator is approaching pi minus pi, which is 0. So the form is 0 over 0. Again, that's an indeterminate form. The limit still may or may not exist. We don't know yet. But this is one of the forms where we can use L'Hopital's rule. Okay, so let's take the given limit, and we'll say it equals to this new limit, x still approaching pi. Now in the numerator, we want the derivative of cosine of x over 2. So that's a composite function, so we need to use the chain rule. The outer function is cosine, and the derivative of cosine is negative sine. And you keep the inside part the same, x over 2. Then we have to multiply by the derivative of the inside part. The derivative of x over 2 is 1/2. Okay, that's the derivative of the numerator. Now in the denominator, the derivative is 1 minus 0, which is just 1. So let's keep our limit sign and just do some simplification before we take the limit. We don't need to write over 1. So the numerator could be written as negative 1/2 sine of x over 2. This is our new limit, so let's think about how we would approach evaluating this limit. Sine is a continuous function, and it's continuous everywhere, so that means it can be evaluated using direct substitution. So all we do now is plug in pi for x, and when we do that we remove the limit sign because we're evaluating the limit now. And then sine of pi over 2 equals 1. Right, so we get negative 1/2 times 1, simplifies to negative 1/2, and we have our limit for this one. When we first saw L'Hopital's rule, it was framed as a limit as x approached a finite number a. But the rule still works for other types of limits, including one-sided limits if x is approaching a finite number a either from the right or from the left. And it also works for limits at infinity, where x is approaching either plus or minus infinity. So having said that, let's look at this next example. In this limit, x is approaching infinity, so we know we can't use direct substitution. So in this case, it might help to think about the numerator and the denominator separately. So let's think about the numerator first. As x goes to infinity, x cubed clearly goes to infinity. And then 2x would also be going to infinity, and plus 4 would just stay 4. So we have something going to infinity plus something else going to infinity plus 4. So as a whole, that sum is obviously going to infinity. Now let's look at the denominator. So as x goes to infinity, the exponent here gets bigger and bigger, which means e to the 2x gets really big. It's also going to go off to infinity, and plus 1 is still going off to infinity. So the denominator is also getting infinitely large. So the form, numerator and denominator both going to infinity, would be infinity over infinity. And this is one of the two forms where you can use L'Hopital's rule. Okay, so let's now apply the rule. So we'll take our original limit and we'll say it equals this new limit, x still approaching the same thing, infinity. Now in the numerator, we need to take the derivative of the original numerator, so that would be 3x squared plus 2. In the denominator, we take the derivative of the original denominator. So for e to the 2x, the derivative would be itself times 2 using the chain rule. Now let's evaluate again what's happening. So as x goes to infinity, the numerator, this term is getting infinitely large, plus 2 is still going to infinity. So numerator is going to infinity. Denominator also would be going to infinity, right? Just like we discussed on the previous fraction. So we have another form, infinity over infinity. So it's still in the form where you can use L'Hopital's rule. So we're actually going to use L'Hopital's rule a second time. Okay, so now let's rewrite this as a new limit as x goes to infinity. The numerator will be the derivative of this numerator, so that will be 6x plus 0, so it's just 6x. In the denominator, we take the derivative of this, so we carry along the 2, and then the derivative of e to the 2x is e to the 2x times 2. So when we multiply by 2, this becomes 4. So 4e to the 2x. And then if you wanted, you could simplify the 6 over 4. I don't think it's really going to make a difference. So let's just evaluate again what's happening with our limit. As x goes to infinity, 6x also goes to infinity. And the denominator e to the 2x also goes to infinity. So we're still in the infinity over infinity case. So we can use L'Hopital's rule a third time. This happens often where you have to use the rule repeatedly. And you might start to wonder, are we ever going to get there, or is it just going to continue doing this forever? But what we want to notice here is every time we use L'Hopital's rule and we take a derivative, notice in the numerator, every time the degree goes down by 1 when we take a derivative. We went from x cubed to x squared to x. The next time we take a derivative, the numerator will be 6, and that's going to be the key to finishing this because the numerator becomes a constant. So let's see how that works. So now, continuing on, rewrite our new limit. The numerator, as we just said, derivative of 6x is 6. In the denominator, we carry along the 4. Derivative of e to the 2x is 2 times e to the 2x. And then the 4 times 2 becomes 8. So altogether, that's 8e to the 2x. Now let's look what happens. The numerator is a constant, so we would just say the numerator approaches 6. And the denominator is still going to infinity. This is now a determinate form, 6 over infinity, right? Anytime you get a non-zero over infinity, that means the fraction is going to 0. So we know we are going to be able to finish at this point. So this limit is equal to 0. Okay, so we got to practice a few new things here. One was how to that you could still use L'Hopital's rule if the limit is as x goes to infinity, as long as this is the right form, which it was. It was an infinity over infinity form. We also saw that you might have to use L'Hopital's rule multiple times before you finally get it to a limit that you can evaluate. Right, once we got to this point, we saw that it was the form was a non-zero over infinity. Okay. Actually, for infinity, it doesn't. If 0 over infinity would also be fine, right? So any number other than infinity over infinity pulls the fraction to 0, right? Imagine the fraction, the denominator of the fraction getting bigger and bigger and bigger makes the whole fraction get pulled towards 0. So we've seen two indeterminate forms where L'Hopital's rule can be used. and that's 0 over 0 or infinity over infinity. There are other indeterminate forms, and I've listed those here. L'Hopital's rule can't be used directly for these forms, right? It can only be used for the two forms we discussed earlier. So how do we handle these indeterminate forms? We're going to learn specific methods for how you can convert these forms into one of the forms for L'Hopital's rule. So we'll go through these one at a time and learn the methods for doing that. But first I want to discuss why these forms are indeterminate. So let's look at 0 times infinity. So you have a product of two functions of x, and in the limit the first factor is going to 0, the second factor is going to infinity. So the question is, what is the product approaching? And you can see these two tendencies are competing against each other. The first factor, getting closer to 0, pulls the product closer to 0. The second factor, getting infinitely large, pulls the product to infinity. And so there's that competition, and we don't know which one's going to win, so that makes this indeterminate. Another is an indeterminate difference. So you have subtraction, or it could be addition, either one. And let's say it's addition, and the first term is getting infinitely large, and the second term is approaching negative infinity. So what does the sum of those, what would that be approaching? You can see again there's that competition. The first factor, getting infinitely large, is pulling the sum towards infinity. But then the second factor, approaching negative infinity, pulls it to negative infinity. And so there's that competition. They're pulling it, the sum is being pulled in opposite directions. If the first factor goes faster, it's going to win. If the second factor approaches infinity or negative infinity faster, it's going to win. Or they might balance each other out and approach some finite number. So again, that's indeterminate. There are three indeterminate powers. So one is you have one function of x raised to another function of x, and the base is approaching 0 and the exponent is also approaching 0. So again, there's that competition. The base approaching 0 pulls the whole exponential expression towards 0. But the exponent approaching 0, you've probably seen the rule that any non-zero raised to a 0 power is equal to 1. So the exponent approaching 0 pulls the exponential expression to 1. So they're pulling in not to the same number. So that would be indeterminate. The next one, infinity to the power 0. So if the base is getting infinitely large, that tends to pull the fraction to be, or the exponential to be infinitely large. But the exponent approaching 0 pulls the expression to 1. So again, they're competing. And then the last one, 1 to the infinity. So if the base is approaching 1, that pulls the whole expression to 1, right? Because 1 to any power is 1. But the exponent approaching infinity pulls the fraction to be, or not the fraction, the exponent to be infinitely large. So again, they're not pulling to the same number. So now we're going to go through these different types of indeterminate forms and learn the methods that can be used to convert these into a form where you can use L'Hopital's rule. Let's start with the indeterminate product, 0 times infinity. So here you'd be considering the limit of some product of two functions of x, where one of the functions limit is 0 and the other is tending towards plus or minus infinity. So that results in this form. We call this the form, right? 0 times infinity. We discussed those two limits are competing against each other, so that it's unclear what the product will be approaching. So here's the strategy for dealing with the form 0 times infinity. You take your product, which we've called f times g, and you rewrite it by forcing it to be a fraction. So one way to force that to be a fraction is to move g to the denominator, but as its reciprocal. So f over 1 over g is the same as f times g, but now it's written in the form of a fraction. Or the other option is you could move f to the denominator by putting its reciprocal in the denominator. So two different ways you could rewrite f times g as a fraction. Now when you do this, the new fraction that you've written, either here or here, will be one of these two types. And those are the types where you can use L'Hopital's rule. In this example, we're asked to evaluate this limit of the function x times log x, and x is approaching 0 from the left. So notice that the function is actually a product of two functions of x. So the first factor, x, we need to figure out what it approaches, and then the second factor, natural log x, also figure out what it's approaching as x goes to 0. So the first one's clear, right? Because we're told x is approaching 0 from the left, and the question is, what is x approaching? Well, it's also approaching 0. Now think about natural log x. It might help to visualize the graph, right? We're familiar with this graph from pre-calculus. It crosses the x-axis at 1, and this is the shape. It has a vertical asymptote right on the y-axis. Okay, so this is the curve y equals natural log x. Now looking at that graph, let's see if we can figure out the limit as x approaches 0 . And I just noticed there's a typo there. That should not be from the left, it should be from the right, because the natural log function is undefined for x is less than 0. So change the problem to x approaching 0 from the right. Now let's go back to our graph of natural log. As x is approaching 0 from the right means we're coming along this way. So following along the curve, notice it's going downward negatively far as it gets closer and closer to that vertical asymptote at x equals 0. So the log x function values are approaching negative infinity for this limit. So the form here, we have a product. One factor is going to 0 and the other is going to negative infinity. It's not 0 minus infinity, it's 0 times negative infinity. This is the indeterminate product we were just talking about. And so we introduced the strategy. So we're going to continue on here with our limit. And we're going to rewrite the function that's given here, this product, as a quotient. So we have two choices. We could either leave the log x in the numerator and then put the reciprocal of x in the denominator. So let's just list those over here. So if we do that, we would have natural log x in the numerator, and the denominator would become 1 over x. The second choice is to keep the x in the numerator and put the reciprocal of natural log x in the denominator. Both of these fractions are equivalent to the function x natural log x. They're just rewritten in a different way. So we can use either one, right? If we use the top one, let's think about the numerator and denominator separately, again as x approaches 0 from the right. We know natural log x would be approaching negative infinity. So the form here, we'd have negative infinity in the numerator, and the denominator 1 over x. So as x approaches 0, the form there would be 1 over 0. And a non-zero over 0 means it's going to infinity. Right? So 1 over x would be approaching infinity as x goes to 0. So we have an infinity over infinity form, which means we could use L'Hopital. Now let's look at the second choice. The numerator is x, so as x goes to 0 from the right, the numerator would also go to 0. The denominator, let's think about this one. We've already discussed that natural log x is approaching negative infinity. So we've got 1 over negative infinity, right? The denominator getting larger and larger makes the fraction go to 0. Okay, so the bottom would be going to 0 when we put all those pieces together. So this one is the 0 over 0 form, which we could also use L'Hopital's rule. So this will always happen with your form 0 times infinity. If you rewrite it in either one of these ways, you'll get one of these two forms where you can use L'Hopital's rule. So how are we going to choose which one to use? In theory, you can use either one, but usually one choice is easier to work with than the other. So if you look at this second choice, when we apply L'Hopital's rule, we'll take the derivative of the numerator, which is easy, but the derivative of the denominator is a little bit messy, right? You'd have to use maybe the quotient rule, and the denominator is natural log x, which is not the nicest function to deal with. Compare that to the choice 1. The derivative of the numerator is easy, right? We know the derivative of natural log x. And the derivative of the denominator is a lot easier than the denominator for the second choice. So we're going to choose this one, just because it looks like it might be a little bit easier to apply L'Hopital's rule. So back to where we left off, we're going to now rewrite our limit of our function by making our function in choice 1 form. Okay, and we just discussed this is the form negative infinity over infinity. So we know we can use L'Hopital's rule on this. So using L'Hopital for the next step, I'll just put L'Hosp. We have a new limit. Now in the numerator, natural log x, the derivative of that is 1 over x. Now look at the denominator. You could use the quotient rule to find the derivative of 1 over x. But we see this one so often, let's just get familiar with it. So I'll work on this over here. The derivative of 1 over x. It's a little easier to avoid the quotient rule by, before you take the derivative, rewrite 1 over x as x to the negative 1 power. Then apply the power rule. So you bring the negative 1 down in front, reduce the power by 1, so the new power is negative 2. And then if you wanted, you could rewrite this using moving the x to the denominator and making the power positive, so negative 1 over x squared. So let's fill in that work here. In the denominator, the derivative is negative 1 over x squared. Now, it's still a little complicated to try to take the limit. So in the next step, we're not going to take the limit, so I'm keeping the limit sign. And we're just going to simplify what's inside the limit. So dividing by a fraction is the same as multiplying by the reciprocal. So we take the numerator as it is, and then we multiply by the reciprocal of the denominator, which is negative x squared over 1. Now we can cancel, so we're still not taking the limit, we're just simplifying. So we've got a negative sign, and then one factor of x will cancel. So we're left with one factor of x in the numerator and just 1 in the denominator. So it simplifies to just negative x. Now we're taking the limit of a polynomial. Those are easy because you can always evaluate those with direct substitution. So we plug in 0 for x, we get negative 0, which of course is just 0. So we got to our limit of 0 for this one. So remember, in this type of product, one factor going to 0, the other going to infinity, they're competing against each other. The one going to 0 is pulling the product towards 0. The one going to infinity is pulling the product towards infinity. So one of them might win out. In this case, the 0 won out, right? Because the product ended up tending towards 0. So that means that x is going to, as x goes to 0 from the right, the factor x is going to 0 faster than log x is going to negative infinity. Here's another limit. This time x is going to infinity, and we're taking the limit of x times sine of 1 over x. So you can see this is a product of two functions of x. So let's look at each factor, and see what they're approaching individually. The first one's easy, right? As x goes to infinity, the first factor x would also go to infinity. The next one we'll have to think a little bit more. So first figure out what 1 over x is doing. So as x goes to infinity, 1 over x would be going to 0. So then we have sine of something that's going to 0. So it's approaching sine of 0. But sine of 0, we happen to know, is 0. So the form of this limit, we have one factor going to infinity multiplied by a factor that's going to 0. And this is the indeterminate product we've been discussing. Okay, so we know the strategy for this. We're going to rewrite our function as a fraction. Our product will be rewritten as a fraction. So one option is to keep x in the numerator and move the sine function to the denominator, but we would have to put its reciprocal in the denominator. The other choice is to keep the sine function in the numerator and then put the reciprocal of x in the denominator. Okay, so again, one choice was to keep the x in the numerator, put the reciprocal of sine in the denominator. The other choice was the opposite, keep the sine function in the numerator, put the reciprocal of this x in the denominator. Now think about which one's going to be easier to apply L'Hopital's rule. Choice 1, look at the denominator. We would have to take the derivative of that, which is pretty messy. The second choice is easier because we don't have to deal with 1 over a complicated function. We still have that complicated function, but at least it's not 1 over that. You don't have to use the quotient rule here. So I think the easier choice here is definitely the second one. We're going to choose that form. So let's come back to our limit. We're going to rewrite it, keep the limit sign, and we decided to use choice 2. So our numerator will be sine of 1 over x, denominator will be 1 over x. Now this should be a form to use L'Hopital's rule, but let's check this. So here, the numerator, so we did this once, right? We said sine of 1 over x is approaching 0. So the numerator is approaching 0. And then 1 over x is not listed here, but we know as x goes to infinity, 1 over x would go to 0. Okay, so both numerator and denominator are going to 0. So the form here is 0 over 0, so we can use L'Hopital's rule. Right, you always want to check that it's the right form before you apply L'Hopital's rule. It has to be one of the two forms, acceptable forms. So now using L'Hopital, we have a new limit. In the denominator, we want the derivative of 1 over x. Now we just saw that on the last example, right? We rewrote 1 over x as x to the negative 1 and applied the power rule. Simplified it, we got negative 1 over x squared. Now the numerator is going to require a little side work to to get that one. So the derivative of sine 1 over x. That's a chain rule problem because we have an inside function where we normally have x, we have 1 over x. So using the chain rule, we start by taking the derivative of the outer function. So the derivative of sine is cosine. Keep the inside part. Now we multiply by the derivative of the inside part. So the derivative of 1 over x, we just saw that, it's negative 1 over x squared. Okay, so there's our little side calculation. And that, again, is what's going to go in the numerator because we take our original numerator, compute its derivative, put that here. When I put it there, I'm just going to write it slightly differently. I'm going to write negative 1 over x squared times cosine of 1 over x. We're still not ready to take the limit because that looks really complicated. But notice there's a nice simplification. This factor, negative 1 over x squared, cancels between the top and the bottom. So when we cancel those, now we have limit. And all that's left is cosine of 1 over x. Now we can't do direct substitution because x is going to infinity and we can't plug in infinity. But let's think about the pieces, right? So 1 over x, we've already discussed, as x goes to infinity, 1 over x goes to 0. So this limit will be equal to cosine of 0. And we happen to know cosine of 0 is equal to 1. So now we're done. We have the limit of the given that we were asked to evaluate. Another indeterminate form we mentioned earlier was an indeterminate difference, which had the form infinity minus infinity. Right? We discussed how those two tendencies are pulling in different directions. The first term is pulling the difference infinitely large. The second term is pulling it infinitely small. So one of them might win out or they might balance. So basically you would be taking a limit of this type where you have a difference and f and g are both approaching infinity, but the minus sign means we have form infinity minus infinity. So the form enough is not sufficient to tell you what this limit is. So the strategy for dealing with these is to try to rewrite f minus g as a fraction. And how you're going to do that depends on what it looks like. 3 common strategies you can take to do this. One is to try to get a common denominator. Right, if one or both of these is already in the form of a fraction, you could do that and combine them then into one fraction. Another would be rationalization. So if you had a square root expression in the denominator of one of those, you could use that method of rationalizing the denominator. Third is if there's a common factor between f and g, factor it out and see if that helps you to write it as a fraction. This example, we have limit of a difference, but let's see what the form is by looking what each individual term in that difference is approaching. So we need to figure out what 1 over sine x is doing and what 1 over x is doing. Oops, sorry, I went too far there. So as x goes to 0, clearly 1 over x would be going to infinity. Now we don't know yet if it's plus or minus infinity. We'll talk about that in a minute. Right, so a non-zero over 0 is always going to infinity. What about sine x? So as x goes to 0, first let's figure out what sine x is doing. Well, it would be approaching sine of 0, since x is going to 0, which is equal to 0. So back in this fraction, the numerator is going to 1, denominator is going to 0, the whole fraction would be going to infinity. Now again, we don't know yet whether it's plus or minus infinity. So to figure out the sign of those infinities, we need to know the sign of, for example, the sign of 1 over x. So as x goes to 0, right, let's look at a number line. This is our x-axis. So as x goes to 0, if x were coming from the right, the x values would be positive, which means 1 over x would be positive, and we would say plus infinity. But x could also be approaching 0 from the left, where x's are negative. So then the 1 over x's would be negative, which means in that case the limit is negative infinity. So we're going to need to consider left and right limits separately. So let's do limits as x approaches 0 from the right first. So let's look at 1 over sine x, what it's doing, and then we'll look at 1 over x. The 1 over x is easier, so let's do that one. We already know it's plus or minus infinity, but when x approaches 0 from the right, that means x is positive. So 1 over x is positive, so it has no choice but to be positive infinity. Now let's look at the 1 over sine x. Let's look at the sine function. Right, the sine wave starts at the origin and then it moves up, and then you can continue it on the other side, right? So we're considering the limit as x approaches 0 from the right. So that means we're coming along here where the sine values are positive. So if sine is positive, 1 over sine is positive, and so the limit has to be, between the two choices, it has to be plus infinity. So the form in this case would be plus positive infinity minus a positive infinity. That's our indeterminate product. But we also need to consider the limit from the left side, right? Because the limit we were asked to find is not one-sided, but we couldn't figure it out just as a plain limit, so we're breaking it down, but we have to consider both. Okay, so same thing, we need to figure out what 1 over sine x is doing and what 1 over x is doing. Let's start with 1 over x. So as x approaches 0 from the left, that means x is taking on negative values. So 1 over x would be negative, which means our choices are plus or minus infinity. Since they're negative values, it has to be negative infinity. Now let's look at the 1 over sine x. So first look at sine. As x approaches 0 from the left, notice the sine is taking on negative values. So 1 over sine would also be negative. So that means we have to choose negative infinity for the limit here. So now the form, the first term is approaching negative infinity, and then we have minus the second term, which is also approaching negative infinity. And minus a negative is a plus. So this is negative infinity plus infinity, which is the same thing as saying infinity minus infinity, if you flip the right and left. So in both cases, we end up with the indeterminate form infinity minus infinity. So this is the form we were just talking about, and our strategy is to try to rewrite the original difference as a single fraction. Okay, so we'll work on that on our next slide. This example is another limit of a difference. Let's look at each term individually. So here we're letting x go to infinity, so e to the x would also go to infinity. And then this x, of course, would go to the same infinity, right? So overall, we have something going to infinity minus something else going to infinity. So the form here is infinity minus infinity. And this is the indeterminate difference we've been talking about. So the goal here is to rewrite it the function here, we want to rewrite that function as a quotient if possible. So we talked about 3 possible ways of doing that, and one is to get a common denominator. But that's not really obvious here because neither one of these terms is a fraction. So it's not obvious how to get a common denominator for this. Another option was factoring, but if you look here, there are no common factors. But even though there are no common factors, you can still try factoring. So here's what I'm going to suggest. Keep our limit sign. Now one of the terms is x, so I'm going to say, well, what would happen if I factored out x? So it'll be something minus 1, right? Well, to figure out what's left here after you factor out x, right? Whatever you factor out, to find what's left inside down here, you divide each of these by whatever you factored out. So if we factored out x, we need to take e to the x divided by x is what's left. And then we already have the second term, right? X over x is 1, so there's the 1. And you can check yourself by distributing the x back. Make sure you get the same thing as the original, and you do, right? So now we have a product. Now let's look at each term in the product. The first factor, x, is clearly going to infinity since x is going to infinity. This one's a little more complicated. The numerator would be going to infinity. Denominator would be going to infinity. And that's an indeterminate form. So it's a form where you can use L'Hopital's rule just to find that limit. So now we're going to have to do a fair amount of side work to find that limit. And then the limit of a constant is just a constant. Okay, so let's write out some of what we just said. The first factor is x, and that limit would be infinity. The second factor in our product is what's in the parentheses there, e to the x over x minus 1. We need to do some work to find that limit. So we'll break it into pieces. First, let's just find the limit of e to the x over x. So as x goes to infinity, as x goes to infinity, note that both the numerator and denominator are going to infinity. So the form here is infinity over infinity, which means we can use L'Hopital's rule. Okay, so we'll write a new limit. In the numerator, we take the derivative of e to the x, which is e to the x. The denominator is the derivative of x, which is 1. So before we take our limit here, let's just simplify. E to the x over 1 is the same as e to the x, and then we've already discussed that limit is infinity. So now let's piece things together. We just determined this limit is infinity. So what's the limit of this whole thing? Infinity minus 1 is still infinity, right? So our answer here is this limit is infinity. So that tells us in our product, right, this term's going to infinity, and the second factor is also going to infinity. So we're multiplying two numbers that are both getting infinitely large. Therefore, the product would also be infinitely large. So our final answer is this limit is infinity. Okay, so the form, if you wanted to say the form of this limit is infinity times infinity, if we write that out, this is a determinate form, right? It's not indeterminate. We know exactly what's happening, if you take two numbers that are, or two functions that are both approaching infinity and multiply them together, it's even bigger, right? So it's definitely infinite. So this is a determinate form. Which allows us to conclude the limit without having to use any other special technique. The form is enough to figure out that limit. So next we have some more indeterminate forms that we call indeterminate powers. We mentioned these earlier. So these happen when you're taking the limit of a function of x raised to another power that has x in the power. And if the base part, the function f, is approaching 0, and then also the exponent is approaching 0, we call that type 0 over 0 to the 0. If the base is approaching infinity and the exponent is approaching 0, then it would be type infinity to the 0. And finally, if the base is approaching 1 and the exponent is approaching plus or minus infinity, it's type 1 to the infinity. So we discussed earlier why these forms are indeterminate. So now we want to look at the strategy for how to deal with these situations. So what we do is we start by letting y equal the function that we're taking the limit of, which is f raised to the g power, and then take the natural log of both sides. So on the left you'll have natural log of y. On the right you'll have natural log of this exponential expression, but then you can use the power a property of logs that lets you bring the power down in front. So originally this was log of f to the power g, but the g has been brought down in front. Then L'Hopital's rule can be used to take the limit of log y, replacing log y with this, because in any of these three cases, this product will be a type where you can then use L'Hopital's rule. Let's look at this limit. We're letting x approach 0 from the right, and we have an exponential expression where we have a function of x raised to a power that's also a function of x. Let's take the limits separately. So for the base, as x goes to 0, 1 plus x will approach 1. So the base is going towards 1. Now the exponent is 1 over x, and as x approaches 0, that fraction will go to infinity. And notice it's a one-sided limit. Since x is approaching 0 from the right, we can actually say we know the x values are all positive, so it's actually approaching positive infinity. So the form here, we decided the base was approaching 0 and the exponent was approaching positive infinity. And that's one of the three indeterminate powers that we were just reviewing. Okay, so the strategy we gave for this is to start by letting y equal the function you're taking the limit of. So 1 plus x to the power 1 over x. Then take the natural log of both sides. So on the left we'll have natural log of y. On the right we'll have natural log of this exponential expression. But then you can use the the property of logs that says you can bring the power down in front. So 1 over x multiplied by natural log of 1 plus x. So what we're going to do now is actually take the limit of natural log y. Now the limit will be the same as the original, so as x approaches 0 from the right, of natural log y. This is not going to give us the final answer, right? Because what we're actually wanting to find is the limit of y itself, right? Because y is this function we're taking the limit of. So this is just an intermediate step. So once we find this, we'll be able to piece things together to find the limit of y itself. Okay, so the next step is we're going to replace, in our limit here, we're going to replace natural log y with the expression we found for natural log y, right, which is over here. Okay, so 1 over x, natural log 1 plus x. So this is a product of two functions of x. So let's look at each factor. One of the factors is 1 over x. The other is natural log 1 plus x. So as x goes to 0, 1 over x will go towards 1 over 0, which means it's going towards infinity. And just like before, since x is approaching 0 from the right, we know x is positive, so it's approaching positive infinity. Now what about this natural log? So inside the parentheses, since x is approaching 0, this inside part will approach 1. So then, because log is continuous, we can say this bigger expression will approach natural log of 1. But we all know that natural log of 1 is equal to 0. So we have a product here where one of the factors is approaching infinity and the other is approaching 0. That is what we call the indeterminate product we discussed earlier. And we had a specific strategy for that, and that is to rewrite this product as a quotient by bringing one of the terms down to the denominator as its reciprocal. Okay, so we're still not taking the limit, so now equals, keep our limit sign. Now I'm going to choose to bring the 1 over x to the denominator because its reciprocal is x. The new denominator will just be x, and that will keep that pretty simple. So we'll keep the natural log term in the numerator, and then we move the 1 over x to the denominator, but we put its reciprocal down here, which is x. Now look at the form here. So we've already said the numerator was this expression. It's approaching 0. So the form here, we have 0 in the numerator. And then the denominator is pretty straightforward. As x goes to 0, this x also goes to 0. Notice now we have it in the form where we can use L'Hopital. Okay, so in our next simplification, we're rewriting it as a new limit. In the numerator, we take the derivative of natural log 1 plus x. So that's a chain rule problem, right? If it were just natural log x, the derivative would be 1 over x. Okay, so the outer function is natural log. We're taking the derivative of the outer function first. So 1 over x, but we have an inside part that replaces x. Then we multiply by the derivative of the inside part, but that's just 1, so we don't even have to write it, multiplying by 1. So that finishes the derivative of the numerator. Now our new denominator will be the derivative of x, which is just 1. And then before we take the limit, let's simplify. We don't need to write the whole thing over 1, right? So it's just 1 over 1 plus x. This is rational, so we can try direct substitution. And notice when we do that, we get, plugging in 0 here, we get 1 over 1. Since we got something that's defined for a rational function, that means that is your limit. You can use direct substitution. Okay. Now, what did we just find? We found the limit, as x goes to 0 from the right, of natural log y is equal to 1. So don't think you're done at this point, because we wanted to find the limit of this, which is y, but we actually have the limit of natural log y. So now to frame it back in terms of the original problem, just to make it clear, I'm going to write the original limit here. Now I'm going to keep my limit sign. Okay, and then rewrite this as y, right? That's what we called y, the function we're taking the limit of. And then I'm going to do a little trick here. I'm going to rewrite y, so keep my limit sign, as e to the power log y. And that just uses the property that e and natural log cancel each other when they're in a power relationship like this. And so this expression that I just wrote actually equals y, which is what we replaced here. So that's the trick. You have to know that's your strategy ahead of time. Now I can use what I know from over here. Natural log y is approaching 1, so this exponent here is approaching 1. So the overall limit here will be e to the power 1. So I'm now taking the limit, so I don't write the limit sign. And then, of course, that's equal to e. So that's the limit value that we were asked to find. Okay, so just to review this strategy, when you have one of these indeterminate powers, this method will always work. You let y equal the function you're taking the limit of. You take natural log of both sides, and on the right side use property of logs to bring the exponent down in front. Then you take the limit with the same x approaching the same number of natural log y. And you can replace natural log y with the expression we found from here. This should be in a form where you can use L'Hopital's rule, or you might be able to rearrange it into a form where you can use L'Hopital. In this case, it turned out to be an indeterminate product, infinity times 0, so we knew if we rewrote it as a fraction, we'd be able to use L'Hopital's rule. So we did that. We rewrote it as a fraction. It turned out to be the form 0 over 0, which confirms we can use L'Hopital. And then we applied L'Hopital's rule. We got to our limit. But then we realized we're not done, because this is the limit of natural log y. We need to find the limit of y, right? Because limit of y is the limit we were asked to find. And then here's the other trick. Rewrite y as e to the power natural log y. Now we can take the limit because we know the exponent is approaching, in this case, 1. So we just use direct substitution, replace that exponent with 1, and then we've arrived at our final answer. So let's summarize what we covered today. We covered all of section 4.4 on L'Hopital's rule. We started by talking about what determinant forms would be. So there are certain situations where you can look at the limits of the various parts of the function, and that is enough to tell you what the limit will be just by seeing the form. So examples of this would be a non-zero over 0. We know that would be going to infinity. Or you could have a finite number over infinity. We know that limit overall would be going to 0. Those are examples of determinant forms. Then we looked at our first two types of indeterminate forms, 0 over 0 and infinity over infinity. Those forms are not enough to tell you what the limit will be or whether it exists or not. But these are the only two forms where you can actually use L'Hopital's rule. So we learned how to apply the rule to limits of these forms. But then we learned about some other indeterminate forms. One was the indeterminate products, which is the form 0 times infinity. And we learned a specific method for how to rewrite that product as a quotient, and then it's in one of the two forms where you can use L'Hopital's rule. We also looked at indeterminate differences. So this is the form infinity minus infinity. And we saw there are techniques that often work with these to rewrite that difference as a single quotient. And that quotient has the form where you can use L'Hopital's rule. And then finally we learned 3 indeterminate powers. And we had a specific method for those that involves using the natural log, right? It's kind of a multi-step process. So that summarizes our work using L'Hopital's rule. So this was back to looking at limits, but we saved it for this chapter because it involves taking derivatives, which we didn't know when we were first doing the chapter on limits.